In this video, we are going to show that an estimator mu hat, if it's unbiased, then its variance is minimized when A1 is equal to A2 equal to AN equals 1 over N. So this is basically the same as saying proof that X bar as a estimator for mu hat will have the smallest variance among all estimators for mu. Now, given the information in the question, we have by definition biased of mu hat is equal to the expectation of mu hat minus mu, and it has to be 0 in order to be unbiased. So we distribute expectation, we get the following. This implies that A1 plus A2 plus AN times mu minus mu is equal to 0, which means from A1 plus A2 plus AN is equal to 1. And this is later become the constraint. Now variance of mu hat is equal to variance of the mu hat, which is equal to by the property of the variance, you can just pull out A1 and square it outside because it's a constant, and then do the same for each terms, and eventually you will get A1 squared plus A2 squared plus AN squared times the sigma square, which is the variance of each xi. Now we come to the Lagrangian multiplier. So the function is with variables a1, a2 to an is equal to a1 squared plus a2 squared plus an squared. And with the constraint we derived from the previous steps, we get a1 plus a2 plus an equals 1. So we use Lagrangian multiplier. The Lagrangian function is arrow a1, a2 to an, and lambda. These are the variables. So we plug in the function over here, subtract by lambda times the constraint, and remember we have to set this equal to 0, and which means we have to subtract 1 on both sides to be 0. So we have it here. Now we take partial derivative of the function and with respect to each individual constraint, individual variables. So the partial of error with respect to a1 is equal to 2a1 minus lambda, because you can treat a2 to an as other constants. And we do the same thing for a2 and an and lambda. So when we take the derivative with respect to lambda, we have this thing. So over here we can see that a1 plus an is equal to 1. And now, based on the previous steps, we derived that 2a1 plus 2a2 plus 2an is equal to lambda times n, which means that a1 plus a2 plus an is equal to lambda times n minus divided by 2, and that is also equal to 1. So from here we get lambda equal to 2 divided by n, and also we go back to the partial derivative. We notice that 2a1 is equal to lambda, which is 2 over n, which means a1 is 1 over n, and so is a2 and an. And this is the end of the proof. Thanks for watching, and if you liked the video, please subscribe below. Thank you so much. Give it a thumb up. Thank you.